Alright, this video is going to focus on formal charge and resonance, and hopefully you'll see why it'll help you with formal charge to determine which resonance structure is the most stable. Um, Formal charge basically looks at how many valence electrons an element contributes to a molecule and determines how many electrons are actually assigned to that element once the Lewis structure is drawn. And the closer those formal charges are to zero, the more stable that atom usually is. So the closer we can get all the elements in that molecule to zero with their formal charges, the more stable as a whole that Lewis structure will be. To calculate formal charge, we determine how many valence electrons the element has, and we subtract from it the total number of lone electrons that are assigned to that element, and we also subtract away half of the bonded electrons, since those are being shared between two atoms. So in the formal charge at the top of the picture below, for oxygen, it says that it has a formal charge of -1. Oxygen normally has 6 valence electrons. It has six lone electrons assigned to it, and it also is bonded to the chlorine, so it has 2 electrons that it's sharing. So we take away half of those, and so 6 minus 6 plus 1 would give us -1. Chlorine has 7 valence electrons at the bottom. It only has 2 lone electrons assigned to it, and it has 6 electrons that it's sharing, so 2 plus half of 6 would give me 5, and 7 minus 5 would give me a formal charge of +2. It does not matter whether you subtract away the bonding electrons first or the lone electrons, but you do need to make sure you subtract both of them away from your valence electrons. So, sorry. So in this particular molecule, we have carbon dioxide. If you find the formal charges of the oxygens in the molecule on the left, with the triple bonded O, we'll see that one of the oxygens has a -1 formal charge, while the other one has a +1 formal charge. Those aren't terrible, but if we move the triple bond to be 2 double bonds, we see that all of the elements in that molecule have formal charges of 0. And again, the closer you can get all the atoms in your molecule to have formal charges of 0, the more stable it's going to be. So double bonded oxygens on both sides is more stable. It's also going to make your molecule not be polar. Resonance occurs when you have an example like we just saw with CO2, where you can make more than one valid structure because there really isn't a preference for the bond to be on one side of the molecule more than the other. In this particular example down here with ozone, you can see that one side has a double bond and then the other side has a single bond. There's no particular reason for the central oxygen to double bond with just the oxygen on the right. It has just as much of a preference to double bond with the oxygen on the left. As we talked about in class today, when you have that possibility where the double bond can form on more than one atom and the formal charges are going to be roughly the same, you are going to see this resonance occur, and there's not going to be one particular form picked over the other. This molecule has those electrons basically rotating back and forth. And so basically each side of the molecule has sharing 1.5 pairs of electrons with the central oxygen. And the more you can do that, the delocalized electrons are electrons that are shared between them. And we're going to see that certain molecules, I think one of the ones you did in your lab was benzene, can have many pairs of delocalized electrons, and that just increases that molecule's stability and causes it to have different types of properties when it undergoes reactions. So we're going to look at some formal charges in the previous examples that you've done, and then we're going to do some examples with resonance. So with POCl3, we're going to focus on phosphorus. Phosphorus has 5 valence electrons. It has no lone electron pairs assigned to it, and it has 4 pairs of electrons that are being shared. So there would be 5 valence electrons minus 0 unshared electrons minus half of 8, since there's 4 pairs or 8 electrons that are shared with it. So it would have a formal charge of +1. If we wanted to figure out what made this molecule be neutral, because all the formal charges should add up to equal 0 when we're said and done, I did not ask you to do this, but you could figure it out that oxygen is the other atom with a formal charge other than 0. Oxygen normally has 6 valence electrons. It has 6 lone electrons assigned to it, and it's sharing one pair of electrons. So 6 minus 6 minus 1 would give me a formal charge of minus 1. In B, for BCl3, if we look at boron, boron starts with 3 valence electrons. It has 3 pairs of electrons that are shared with it, so it's sharing 6 electrons and it has no lone electrons. So 3 minus 0 for the lone electrons minus half of 6 would give me a formal charge of 0. And again, the closer we are to 0, the more ideal it is. If we look at chlorine, I did not do chlorine for that one, sorry. Chlorine starts with 7 valence electrons. You're sharing 2 electrons and you have 6 lone electrons assigned to it. So it would be 7 minus 6 minus half of 2. So each of the chlorines would also have formal charges of 0. In carbon monoxide, there's not a central atom, so we're going to do actually both elements. If we look at carbon, carbon normally starts with 4 valence electrons. It has 2 lone electrons assigned to it, and it's sharing 6 electrons. So 4 minus 2 minus half of 6 would give me a formal charge of minus 1. Oxygen has 6 valence electrons. It has 2 lone electrons assigned to it, so 6 minus 2 minus again half of 6 for the triple bond would give me 6 minus 2 minus 3, so 6 minus 5, or in this case a plus 1 formal charge. We're going to draw a couple structures with resonance, sulfur dioxide and sulfur trioxide, and I think that's the end of this particular video. Sulfur dioxide, sulfur trioxide are all made of elements in group 16, so they have 6 valence electrons. So we have 18 electrons for sulfur dioxide. We start by putting a pair of electrons between sulfur and the 2 oxygens. That takes care of the skeleton. Now I'm going to do 6 electrons around each oxygen. That would use up 6, 12, 18. That would use up all but 2 electrons, so those would go on sulfur. That does not give sulfur the 4 pairs, so that's why we need the double bond. Because that double bond formed between the oxygen on the left, there is no particular reason for it not to form between the oxygen on the right. So that would be the other resonance structure for SO2. With SO3, we have 6, 12, 18, 24 valence electrons. This time we're going to have all the electrons be assigned to connecting sulfur to each of the oxygens, as well as having 3 pairs of electrons that are lone electrons assigned to each oxygen. But that would mean the sulfur in the center does not have a 4th pair, so we would use one of the pairs off of the oxygen to make a double bond. Again, there's no particular reason for it to be on one particular oxygen than any other. So sulfur trioxide actually has 3 different resonance structures. You can have the double bond on the oxygen on the right, double bond on the oxygen on the left, or a double bond on the oxygen on the bottom. Okay? So you just always want to look out to see is there anywhere else that double bond, the multiple bond, could go. And it can go pretty much anywhere as long as there's a lone electron pair assigned to that particular atom. Formal charges, however, are a way if the molecule is not symmetrical to determine which structure would be the most stable. Alright, I think that's the end of that particular video for you.